All right, so how far does an object in free fall travel in the first second? So we talked about its speed. Starts at 0. 1 second later, it's at 10 meters per second. 2 seconds at 20 meters per second. But how far does it fall? You know, how far? Now we're talking about distance. So we're saying the initial speed is 0. The average is 5. So during the first second, it's going to be 5 meters. So think about this. We're trying to figure this out. And we know that to find distance is your speed times time. In math, we probably talk about rate times time, or in physics, we talk about velocity times time. But we said our average speed. It's our average speed, in this case 5 meters per second. So 5 meters per second is my average. In 1 second, seconds cancel, I'm left with 5 meters. So that's how far it went in the first second. So if you drop something at any point right now, you can drop something, go stand on top of a building and drop it someplace where it can fall for a whole second. And a normal object that doesn't, one that's not like a feather or something, is going to fall 5 meters in the first second. So here's our rock. Now it has an odometer on it, so we can figure out how far it's fallen with time. So at the end of 2 seconds, it's going to now have gone 20 meters. At the end of 3 seconds, it's going to have gone 45 meters. Okay? Now, how did we get that? Well, here's the formula that we're going to use. Distance equals 1/2 gt squared. Or, if we're talking about any kind of acceleration, just be at squared. But in here, we're talking about specific kind. We're talking about free fall. And so we're going to use g. So 1/2 times your acceleration times the time squared. That's the formula for finding distance given acceleration and time. So in 1 second, you've gone 5 meters, 220, 345, 480, 525 meters. So in 5 seconds, if you jump out of an airplane in 5 seconds, you will have fallen 125 meters. Now think about that. You can run, if somebody really fast might be able to run that 100-meter dash in about 10 seconds. Well, you just went 125 meters in 5 seconds. All right, so here's some formulas for, and personally, these are the formulas I would prefer that you remember, because I always just think I plug in G when I'm doing gravity, but these are more generic. They work for everything. These formulas still work for gravity. We just know what the acceleration is for gravity. And these are just better formulas. So velocity equals acceleration times time, and distance equals 1/2 at squared. Those are 2 key formulas in this particular chapter. And these are talking about acceleration being constant. That's the main thing you need to understand. We're talking about a constant acceleration in here, and we're also talking about the speed starting at 0. We can do it without the speed starting at 0. The formula is a little more complex. You have to add in a little bit more to it. But this is where, if you start at 0, constant acceleration. So let's think about this. An apple drops from a tree, hits the ground in 1 second. What's the speed upon striking the ground? What is its average speed during the 1 second? And how high above the ground was the apple when it first was dropped? I want you to stop the video and I want you to figure those out right now. All right, and there's the answers. When it strikes the ground, it's going to be going 10 meters per second. Remember, the acceleration is always 10 meters per second, so after 1 second, it's going to be going 10 meters per second. I'm sorry, the acceleration is 10 meters per second squared. Now, the average speed, well, it went from 0, the initial, to 10. 0 plus 10 divided by 2 gives me 5. So that's the average speed. So the average was 5, but when it hit the ground, it was going 10. And how far? Well, when we want to figure out how far, we can use the average speed. We said, well, we're going 5 meters per second in 1 second. The average is, or the distance then, is 5 meters. Now, you could still do it. You could also do it with the other formula. So you could do this one. Let's kind of take a look at this. So I could say, well, my distance is my average speed or average velocity times time. That's a formula. And so we would say it's 5 meters per second times 1 second. That equals 5 meters. We could do it that way. We can also do it with distance equals 1/2 at squared. And we put in 10 for our acceleration. 1 squared. Well, 1 squared is 1, so 10 divided by 2 equals 5 meters. So either way, gets you the same answer. All right, so we've been talking about numbers, we've been talking about tables, but a lot of times it's just easier to look at a graph. It's a little more visual when we want to do that. So we're going to talk about graphs. So let's take a look at an example of a speed versus time graph for a freely falling object. We've got speed on the left here, time on the bottom. So if we look at that, notice that in 1 second, at 1 second, we've gone, or our speed has changed to 10 meters per second. In 2 seconds, we're at 20. 3 seconds, we're at 30, and so on. So the curve, anything we draw something on a graph, we call it a curve. That best fits this is simply a straight line. And, they might call that linearity. Now, since it's dropped from rest, we're going to start at the 0 point. We're going to start way in the corner, in the origin. And, if we double the time, we double the velocity. If we triple the time, we triple the velocity, and so on. So it's just this nice straight line. We would call that a direct proportion. In chemistry, we talk about direct proportions when we're talking about like Charles' law. Okay, so as one increases, the other increases. That's a direct proportion. So time and speed are directly proportional to each other for free fall. Now, if we have a straight line, we've got a constant slope, and our slope is simply, take the change, the horizontal change, or vertical change divided by the horizontal change. In other words, change in y over change in x, or rise over run. So for every 10 meters per second of vertical change, we had a horizontal change of 1 second. Therefore, our slope is 10 meters per second divided by 1 second, or 10 meters per second squared. So notice that the slope was what? Slope was acceleration. So in a speed versus time graph, the slope of the graph gives me the acceleration. The steeper the acceleration, or the steeper the slope, the higher the acceleration. If the slope is really shallow, it's not very big, it's not a very big hill, I'm not accelerating by very much. If it's almost straight up, I'm accelerating by a lot. All right, so how about distance versus time? Let's say that we have the distance of a freely falling object, and we'll plot that distance on the vertical axis, time on the horizontal axis. If we do that, we get a curve. We don't get a straight line. We get something that looks like this. In the first second, we said, well, you've gone 5 meters. But it also said, well, after 2 seconds, you've gone 20 meters. And after 3 seconds, you've gone about 45 meters. And so on. And notice it just keeps getting bigger and bigger and bigger. So we don't have a straight line here anymore. In fact, we have a parabolic line. And that's because it's a quadratic curve. It's parabolic because we've got a square involved in this. So if we think about it, if we have distance and we're talking about time, well, distance and time are related, but time is squared, versus when we're doing velocity and time, we just simply had the same power on both. So that's why we get that curve. It looks a little bit different. It's not a straight line. So a curved line also has a slope, but that slope changes from point to point wherever you take it at, and the slope of the curve is going to change. But if we look at the slope of the curve on a distance versus time graph, that's going to give us the rate at which we're going. In other words, it's going to give us our instantaneous speed at that point. Okay? slope steepens as time passes, which shows that the speed increases as we go through that. Okay, so now let's take into account, before we were just talking about object, we didn't worry about air resistance, but let's talk about it now. Because, obviously if I drop a feather and I drop a coin, they don't fall at the same rate, okay? And the reason for that is air resistance affects those two. If you did that in a vacuum, if you went to the moon and you dropped a feather and a coin, they would land at the same time. In fact, one of the first things that they did when they landed on the moon, I think it was in the first one. I'm not sure the first time, for which one. But they took a hammer and they took a feather and they drop it, and they have this on video, and it shows the two objects falling at the same rate. So here we are. We put them in a tube that's a vacuum tube. There's no air in there anymore, and they fall at the same rate. So a lot of times air resistance is small enough. If we're talking about like a baseball or a brick or something, you're not going to really notice it with that. But obviously with a feather, something like that, you're going to see a difference between those two. All right, so here to kind of wrap this up, how fast, how far, how quickly, how fast changes, and so on. So here's the key things. Don't mix up how fast with how far. If we want to know how fast something is falling from a certain rate, we're going to use velocity equals gt. If we want to know how far, we're going to use distance equals 1/2 gt squared. So keep those two in mind. One of the things that I like to do is just make sure my labels cancel. That's why I'm such a big, I always talk about labels. I think they're important. If you start looking at even physics formulas now, if you make sure they cancel, you usually have the right formula if you get your labels to cancel out. If your labels don't cancel, you should absolutely know you have it wrong. If you can't get your labels canceled, you did it wrong. Just absolutely. So they talk about one of the most confusing concepts is acceleration, because we're talking about how quickly the speed or velocity changes. And what makes it complex is that acceleration is a rate of a rate. Okay, so velocity is a rate. It's a rate, it's meters per second. And acceleration is the rate of that, rate. So that gets a little bit confusing. But acceleration is not velocity. Don't get it confused. They're not the same thing. And acceleration is not a change of velocity. Acceleration is the rate at which the velocity changes. And that seems minor, but there's a difference there. Okay, if you want to, I'm going to click through these little things. You can stop it and get the answer, and then check to see if you got them right. This would be a good assessment to see if you guys know what you're doing.